don't know. But good morning. We are going to be working on section 14.6 today. And we're basically looking at what's called directional derivatives. So a directional derivative of, say, a three-dimensional function such as z equals f of xy in the direction of the vector u is given simply by the dot product of the gradient with the direction vector u. U is, as I said, the direction vector, and delta f is the gradient vector. So I'm just going to do one example of, a simple example of that, and then we'll do a situation where we're talking about the direction in terms of an angle theta. What I don't think I spent an awful lot of time in explaining, mostly because it's so difficult to draw, is that, can we imagine that the surface looked like this? It was a flowing hill thing. It's very difficult to draw, but you can imagine it was like a flowing hill. When you talk about the vector u, what you're really talking about is, imagine this point here was the xy coordinate, ends up being on that surface, right? And then on this point on the floor, you go in a direction that is a vector u. So if you're on the surface, and you have to imagine looking vertically down on it. Can you imagine it was see-through or coloured glass that you could see through, right? And you go right down to the bottom. Can you see that the direction is a two-dimensional vector on top of a three-dimensional surface? So as best I can imagine it, can you imagine now going in that direction on the surface P? That's meant to be parallel to that. Can you imagine doing that? And so what the directional derivative is basically saying, at that point, walking in that direction, how steep is the hill, right? So, a slope of 4, right? A gradient or a slope or a derivative of 4, same thing, right? That tells you. If it was negative, wouldn't you be going downhill in that direction? And if it was 0, wouldn't you basically be like a circle? You'd be going horizontal. The surface would be horizontal at that point. So, a little side issue, just for those people who need to visualize what the heck they're doing. So, let's have a function, z equals x squared e to the x plus y cubed. So you can get in the direction vector is, I don't really want to make my life too difficult, so I'll make that 0, because I have no imagination, and 1. Yeah, that's very basic. So we want to find the directional derivative of this particular surface at that point, but going in the direction 3, -1. So what we do is we find the gradient vector, which is basically the partial derivative of this function. So when you write z, it's totally equivalent to just saying f of xy. So this guy's derivative with respect to x is a product rule. It's 2x e to the x plus x squared e to the x, and you can check that out yourself. And then if you differentiate this guy, you get a y cubed cosine x. So that's quite a messy one. And then if you do a partial derivative with respect to y, what do you get out of x squared e to the x if you do a partial derivative with respect to y?
0.
Yeah, so in a way it's a lot easier, the second one. Won't this just be 3y squared sine x?
Yep.
Now, that is the general gradient vector at any given point xy. In this particular question, and pretty much all of them, aren't you given a specific point to calculate it? So this gradient vector in this particular case would be 2 times 0, don't care, it's 0, 0, 0, don't care. Y cubed cosine of 0 is -1 cubed times the cosine of 0, at least that's something. 3y squared sine thingy becomes 3 squared sine of nothing, so that's nothing. So after all that hard work, we end up with the gradient vector is really just 0 or 1, 0. Right? 0, 0, 1, comma, 0. And the direction vector in this case is that guy. So the directional derivative at the given point 0, 1 is that guy. Dot product with this. It's 1, 0. Dot product with 3, negative 1. That gets me 1 times 3 plus 0 times negative 1, and I get the slope of 3. So if I put that into some software and found out what did that surface look like, and then I focused on the point on the ground called 0, 1, and then I went up to the surface, right? So that would be there. And I went in this direction. That direction would have a slope of 3. So at that point, traveling along the surface in the direction 3, negative 1, you would be going uphill with a slope of 3. We're comfortable with the process? Good. So, second kind of question. Let's suppose we do z is equal to cosine of xy plus x squared y plus 3y. And we are interested in the point pi 0. And we want to go in a direction, but the direction is going to be in terms of an angle. So instead of telling you you're going to go in that direction, what you're basically saying is whatever, pi upon 3 is, right? You're going to go in that direction, theta. Well, pretty much the same kind of process. The gradient vector, right? Differentiate this fellow with respect to x. Ooh, okay, that could be fun. Differentiate this vector, that's going to get you negative cosine of xy times the derivative of xy with respect to x, so that gets me a y. So it's negative that guy. This fella here, say again?
Wouldn't it be negative sign, not negative cosine?
Yes, it would be. Thank you. Too busy looking at the next line. With respect to x, and nothing for that. If you do the y, it's going to look very similar. And a 3. So there's the general gradient vector. The gradient vector at pi comma 0.
For that, the y coordinate of the gradient vector, shouldn't that also have plus x squared?
This one here?
No, down at the bottom, the delta f should be negative x sine xy plus x squared.
Here?
Yeah.
Yeah, agreed. Take it slow, I'm going too fast for my good. To remind myself, this is x and this is y. If you plug it in here, don't you get 0, so I don't care about that. If you plug one of them in here, I get 0. So essentially, I can cut a whole load of corners and say it's 0. This guy's going to be 0. X squared is actually going to be pi squared plus 3. Does that look good?
Yeah.
Got to be a bit slower this time, right? Now, the angle theta equals pi upon 3. Basically, that generates a direction vector that looks like that. In this case, the the direction vector is the cosine of pi upon 3, comma, the sine of pi upon 3. I think last time I gave you the formula with the cosine and sine attached, right? And this time I'm just taking a different approach, but it's going to be exactly the same answer. Do you know these two guys are standard angles, right? So we don't write in 0.167 or whatever. So if I draw a little baby right angle triangle, if you make this root 3 and 1 and 2, this guy here is pi upon 3. This guy here is pi upon 6. So if I wanted to know the cosine of pi upon 3, the answer would be 1/2. And if I wanted to know the sine of pi upon 3, it would be root 3 over 2. Are you comfortable with the exact value of these two using that triangle, or you just get a really good memory for them? Now, we're going to put this picture together. The direction vector of this function, x comma y, is going to be delta f dot u. In this case, it's going to be this guy here, dot product with this guy here. And those two get you nothing, and this guy times this essentially gets you root 3 over 2 pi squared plus 3. So I would probably just leave it alone. I don't think there's really anything I can do in this case. So root 3 upon 2 pi squared plus 3 would be considered the exact value of that particular directional derivative. It's about 6 root 3, very roughly. So it's pretty steep. That'll be good. Now, this is not something you're going to get examined on, but I want to try and put some meat on the directional derivative thing. I am not even vaguely any good at drawing. But will you pretend that I have now just drawn the top half of a sphere? Now, spheres are very symmetrical objects, right? You can imagine in a sphere. If I choose a point on the sphere that's quite near the ground, right? Quite near the XY plane, right? So can you imagine a side view of it might look something like this. If I choose a point here, can you see that's roughly the direction vector? You know, if you orientate it a little bit, that's the direction vector. If you go here, can you see that's the direction vector? If you start right at the beginning, couldn't the direction vector be virtually vertical? So as you're traveling along that surface in one particular direction, can you see that the slope of that line is getting smaller? If you reach the top of the sphere, no matter what direction you do, won't you end up with your direction derivative being horizontal? So if you can find a point on a surface that no matter what you do to it, the maximum value of its slope is 0, right? Because no matter which direction I pick, isn't the directional derivative going to be horizontal and the slope of a horizontal is 0, right? Aren't you looking essentially at the top of a hill or the bottom of a valley? So can you see how being able to solve questions like finding directional derivatives might give you a little bit of insight to what's going on in that surface? Is it steep at these places? Is it quite flat at these places? Because won't flat, meaning horizontal flat, won't that be equivalent of like a plateau? if it's flat like a piece of paper going at an angle, won't the directional derivative basically be the same kind of number? Right, whatever the general slope of the line is. So directional derivatives are sometimes used to analyze steepness, for want of a better word, of a surface. Big directional derivatives are saying it's the surface, at least in some directions, is quite steep. So, some insight. So what we're going to do next is I'm just going to make your life harder. No, because, well, let's rephrase it. I'm going to make your life more interesting by giving you challenging situations. So here's our first challenging situation. And we're interested in, at the point 1, 2. And I would like to get the directional derivative of this surface going in the direction 3, -1. Agreed? Now, in this situation, we need to find the partial derivative zx and zy. Agreed? I'm using f of x and fy, but isn't that totally the same thing as zx and zy, right? They're equivalent. But to get the gradient, right, this fella, we have an issue. We need to find these guys, but it's not in a format that would make my life easy. See, if I just said z equals, wouldn't the answer be 2x and minus 2y? Wouldn't be an issue. You can do it in your sleep. But let's look at this problem then. To find the partial derivative with respect to x, we do implicit differentiation. Differentiate z squared gets you 2z dz by dx. Differentiate this guy, you get, with respect to x, you get 2x. And what do you get if you differentiate negative y squared with respect to x?
0.
0. Do you see that guy does not give you negative 2y dy by dx, but this guy does. Do you see that z is treated differently than y is? Right. Now, with a little rearrangement, we get that, which in turn, what am I saying? Nobody caught that mistake, that's a z, which eventually gets us this. Are we good? Cancel the 2's, x in the top, z in the bottom. Now, can I skip some corners here and tell you that if you work on it, you probably won't be surprised that that's the other one. And why do you think that's got a negative and the other one, the x's, didn't?
Because it's minus a y squared.
Right. Now, can you imagine it could be x cubed, y squared, and all sorts of combinations, right? But we've got these two guys. Now, I also have the point 1, 2. But to get these numerical answers, don't I now need to know what the z value is at 1, 2? And this fella, if you plug in x equals 1 and y equals 2, you get z squared. I should have thought of my question. Can we pretend the question was at 2, 1? You get 2 squared, take away 1 squared, you get 3. And so z is going to be the square root of 3. Now, it could also be negative square root of 3, but can I pretend that I tell you it's the top half of the sphere, or the top half of the, actually, that's not quite a sphere, but whatever. It's the top half. So I now have this fella is x, which is called it 2 over root 3, and this fella is going to be y over root 3, and those are the two numbers that I need. So I now have 2 over root 3 and negative 1 over root 3. That's the hard part. Now, if I want to get the directional derivative, we just take the dot product. And this fella with this fella. And this times this gives you 6 over root 3 odd this guy. So it ends up being 5 over root 3. And I'm really annoyed at the book because that's the answer they're looking for.
Isn't it u equals 3 negative 1, the vector?
Oh, darn it. Hey, thank you. I'm really annoyed at the book saying that's a good answer. Shouldn't you rationalize the denominator in something as simple as that? Again, I don't know. It may take that as an answer, but I know it does take the top one. So you're not going to be marked wrong if you do it. So you could have an implicit differentiation situation, and that means that it's going to be much more ugly and much more messy to get this fella. Now, if they didn't, imagine the question didn't tell you it was the top half of the surface, then technically speaking, wouldn't there be 2 directional derivatives? There'd be the one that was plus, and then the other one would be when that one was negative. And so I guess it would be 2 distinct answers. But if that was the case, they would tell you, find the 2 different directional derivatives at this point. I would go with that situation, that sometimes you need to do implicit partial differentiation to get your derivative. Now this one is a bit different. Suppose we have a nice function. I'm not even going to make it particularly ugly. And we're being asked to find the directional derivative at the point 1, 2. And it's going to be in the direction towards 3, 5. Now this one's not anywhere near as messy as the last one, because instead of you telling me the directional vector, haven't they basically said you're starting at P and you're going to Q, but isn't P to Q the direction vector? So if you want to find out who U is, you basically are going to find P to Q. Now, hopefully this is no biggie because you've probably done worse looking vectors than this one. But when you do this, don't you do what I call second take away the first? So you go 3 take away 1, and then you go 5 take away 2. That's how I remember this, right? Second coordinate take away first, second coordinate take away first. And that means that in this particular case, they've really just disguised the direction by telling you a start and a finish point, a P and a Q, rather than telling you just U right off the bat. Well, since I made my life easy here, would you agree there's our gradient vector? Our gradient vector at P
it should be 3y squared.
Keep me on track. At P, we should use this fella. It's 2, 12. And so the 3 times just for check. So the directional derivative is the dot product of those 2. And so it's a 2, 12 with a 2, 3. That's 24. No, it's not. That's 4. And that is 36. Question, Benjamin? No, you're good. Are we comfortable with questions where they don't tell you, they tell you a start and finish point? That's not too difficult to fix. Questions where, and you know, I give you, although I screwed up, a pretty standard, you might have to do implicit differentiation on, right? So let me jump across to the homework so we can just look at some of these questions and see if they work. Now I'll turn this way. I think I noticed last time a lot of you peering very intently, because I'm assuming that on your screen things are a little bit smaller. So I figured a way around it, which I was quite pleased with myself, of enlarging the size of it. Is that easier to read than it was, say, on Friday?
Very much so.
Do you need more, or is that good enough?
No, it looks
I
fine.
think that's good.
Right. So now we can see the questions without hurting your poor eyesight. Can you see this directional derivative is giving you the angle? We covered that today. This directional derivative, an angle again. This directional, an angle. And in this one, you're going to find a gradient, then you're going to evaluate it, and then you're going to do the gradient vector. The textbook seems to like to mix and match I and J's, and I like the, you know, the funny little brackety thing. So I always turn everything into a funny little brackety thing, and that's me. But you know, it's fine. Are we comfortable with that question? Right. Now, what we haven't done, so why don't I use this, or at least part of this as an example, is that we haven't done a question, good, where it's a fourth dimensional function. If we have, I've forgotten that we did. Now, you just extend what you already know, right? So I'm going to go into vectors, and I'm going to choose that guy because I like him. And you do the partial derivative with x, then with y, and then finally with z. So if I did it with x, it would be 2xyz. Comma. And now if I do a partial, no, it's not comma. Take away, with respect to x, yz to the power of 7. Now I can do my comma, right? And then if I go through it with respect to y, I think I just get x squared z for the first piece. And if you do the second guy with respect to y, you pretty much get almost the same thing. But I believe you get one little difference, but it's important. You get that guy. So if you differentiate this term, partial derivative with respect to y, basically the y disappears and you're left with that. And then you go and you do the last one, and the last one gets you x squared y. And what else do you get? And take away 7xy z to the 6. Are you comfortable with what I just did there? Right? It's basically just expanding an fx fy to an fx fy fz, right? Just a three-dimensional, four-dimensional surface, but a three-dimensional vector. Now, I'm not going to do this one, really. I'm going to pretend I'm doing it. And you might not know this, and if it's true, it's a miracle. But couldn't I evaluate this horrible mess when x is 6, y is -1, and Z is 1. And I'll pretend that it's that number, right? But you could evaluate it, right, and get its real value. Then wouldn't this fella here just be the dot product of 1, 2, 3 with this ugly mess up here? And 1 times nothing doesn't harm. That gets you 8/5, and that gets you take away 9/5. So if I was correct, which I highly suspect I'm not, I would just be left with a 1/5. And that's how you would deal with directional derivatives in 3, 4, actually 20 dimensions. It wouldn't really matter. I was listening to a really cool radio broadcast while I was driving on Saturday, and the guy was talking about the latest theories on universe and multiverse. So this guy's like a top-notch leading scientist in theoretical cosmology, I guess you'd call it, right? Cosmology, I don't think you have to put theoretical. And he was telling us that to model the universe that we're in, you have to use 10 dimensions. So those, I know it's probably none of you, but it's kind of interesting to know that they are using the math that we created for them in doing that. So the minute you start working with 10 dimensionals, can you imagine that you might be working with 10 dimensional surfaces as well? And that you might be interested in derivatives, directional derivatives at particular places, given certain, you know, at a black hole or whatever it might be. And they're coming up with some really cool math based on this. So multi-dimensional functions, multi-variable functions are getting used in very, very high level, cool cosmology stuff. And he'd done some really weird things, so I'll just share it because it's out of my head. Do you know that the latest theory is that the universe is actually a bubble in 10 dimensions? And that if you shot a piece of light, and we're on the surface of that bubble, right? So we don't inhabit the inside of it. We inhabit the surface of a 10-dimensional object. If you shone a light from the sun and you projected it in a certain direction, theoretically, it would loop right round and it would hit you in the back of the head. In the same way that we live on the surface of a sphere, right? That's what the Earth is. Theoretically, if you shot a bullet and it was fast enough and you shot it in any direction, wouldn't that bullet hit you in the back of the head? So the curve that we get is caused by gravity. Well, basically, gravity is curving the universe. In the big picture, right? The entire universe is being curved because of gravity. Really weird. And then he talked about multiverses, which says that we're not the only universe in the whatever you want to call it, the multiverse, that there are many universes, and we're just one of them, which I thought is kind of interesting. So I wish I could remember who the guy was. I would tell you, maybe you could find, if you're interested in that thing, you could go hunting for it, because I'm sure he's got a blog or something somewhere.
What's his name? Sean Carroll?
I'm horrible at names. I'll tell you a little bit about what I know about him. He's oh God, keep thinking. He is a professor of cosmology at, fingertips. I believe New York State, but don't quote me on that. I believe that's where it is. So the guy you just mentioned, if that's where he's from, that's fine. But don't quote me on the New York State. I wish I could. I wish I had a great memory, but I've not. But there's only probably a few guys who could be him, because he's at the end of his career, because they went and mentioned that he got his degree in 1986, I believe. See that I can remember numbers, I just can't remember the guy's name. So if you've been teaching, if you've been doing the job for 34, and I'm sure you didn't get your PhD till you were well into your 20s, I mean, the guy is close to retiring. And he wrote a couple of books. Again, I can't remember. And I have drifted far too much. So let's return back to some of the other questions. Are we looking at these? We're still on the same thing, aren't we? The same sheet. Right. Can you see that this one is your classic direction vector point, direction vector point, direction vector point, right? No frills, no nothing. There's a little bit different. Isn't that one going to have to be done in terms of three-dimensional vectors, right? So X, Y, and Z. So is this one. That one's back to 2. This one's 3. Oh, I almost finished. From point P to point Q. Can you see the point P to point Q thing going on as well? So the direction vector in this case would be 3, 4, and the direction vector in this case would be -2, -4, 4. And then that's kind of covered that.
For the problems like number 10, it says v equals something, but that's the normal vector, so you have to use the normal vector to get the unit vector before you can actually do the problem.
Okay, so number 10, although I've cancelled out, says find the directional derivative of a function in the direction of vector v. And you're saying that's a normal vector? Is that what you just said?
Yeah.
Yeah, I think you're reading more into that than necessary.
I already did all the homework though, and if you
Uh-huh.
use that vector instead of making it into a unit vector, then
Oh, a
the problem
unit
will be
vector,
wrong.
yes. I hear you. Right. Yeah. When you said a normal vector, I think you mean a unit vector, don't you?
No.
No? So what would you call the normal vector to 14, 42, 21? What would be equal to?
A normal vector divided by its magnitude is the unit vector, because the unit
Correct.
vector is in terms of 1.
Okay, so what you're calling a normal vector is the unit vector then, isn't it?
No.
If you take a vector and divide it by its length, isn't that a unit vector?
Yes.
So call it a unit vector. To me, a normal vector has a totally different meaning. A normal vector is a vector perpendicular or
Yeah, I know.
orthogonal to another one.
But those vectors that they have written down aren't divided by their magnitude yet, so they're normal vectors still. You have to make the unit vector by dividing it by its magnitude.
You mean regular vector?
Sure.
Okay, I think you guys have done some kinematics and done vector stuff, and you're being given labels to certain circumstances or situations, and you're using a label that is not the label I would use, and that's why I'm kind of arguing with you. I'm only arguing over semantics. In other words, what you call the darn thing. Can you call it a banana if you wanted to, as long as you do it correctly? So
Okay.
we're cool. I still would not use the term that you use, but I can understand that that might well be the term that you're used to using. It has a different meaning to me from the mathematics world. When you say normal, it means something different to me. So that's why the confusion was arising. But yeah, the unit vector is implicit in this question, but technically, when you look at these guys, yeah, that's the case. Right, what was I going to do here? Ah, darn it, time is shot by. Having too much fun.
Should we do
Getting
roll?
Right, let's go. Imagine you have a function, z equals f of xy. In particular, let's just say that guy. I don't want to make my life too difficult. And you're interested at the point 1, 3, which you may well be. And the question that you're being asked to find here is what is the maximum slope at the point 1, 3. So I'll try and screw up. So imagine you've got your surface z of xy, and your surface of xy looks like this again. And you've got a point P, just here. And you project it up to the surface that's here. Now, on that surface, can't you go in any one of 360-degree directions? But could you imagine that there's one specific direction that you get the maximum slope in? And we would like to know what that maximum slope would be, right? And what direction would you need to travel to get that maximum slope? And there's a very interesting property. The maximum slope will happen when you evaluate the gradient vector at the point 1, 3. You wouldn't have thought that, right? So in this case, the gradient vector, let's just do the general one first, is 2x 3y cubed. The gradient vector at the point 1, 3 is 2 and 3, 3, 3, 3, 81. So the maximum slope happens in that direction.
Should be 3y squared.
Yeah. I should slow down more. I'm never going to get things right. Thank you. 2, 27. So can you imagine, I have no idea about 227, but can you imagine 227 is going that way? I'm coming back to that guy, and I'm going to rewrite him again without the mess. And what would the value of that maximum slope look like? Okay, do you use, when you've seen vectors, do you use a single line round something to mean the magnitude of the vector? Or are you more comfortable with the double lines to mean the magnitude of that vector, right? How long a vector is. Which one of those two notations is the one you've seen before?
I think typically the double line.
The double line, is that more? And do you know that a single line does the exact same job, and it depends on what textbook and who you look at? I'll try and be consistent, although I'm sure I'll forget the second line. Now, in this case here, if you want to get the magnitude of that vector, it's basically 4 plus whatever 27 squared is. And I'm going 27 squared, and I'm looking at 729. So square root of 733, and I'm not going to do anything with that. Now, the direction that you travel is called 2, 27, right? That's that red line. It's not uncommon that we convert this into a unit vector. Because, to give you an example, as you know from vectors, if I had a vector 1, 2, isn't 2, 4 the same direction as just twice as long? You agree? That this vector and that vector are both the same direction. That's this vector and that's this vector. But aren't they both pointing in the same direction? Now, since there is an infinite number of directions, right, that you could be pointing at, what one do we typically use? Well, the one that we typically use is the one that's 1 unit long. What I'm going to call the unit vector, and you may have another name for him, like the normal vector or something you called it, at least some of you did. So back to this guy. the direction where the maximum slope occurs is the direction 2 along and 27. The magnitude of that vector we've just found is the square root of 733. So won't the unit vector be 2 over the square root of 733 and 27 over the square root of 733? So when we tell someone the direction vector of the maximum direction, you should always give it in terms of a unit vector, a vector that is 1 unit long. Is that consistent with your idea of how vectors, how you convert something to a unit vector? You're going to find that guy anyway, so you might as well use them up here. So when I do this fella up here, and since the book is being generous, you could probably just leave that as an ugly fraction and not worry about it, because it will accept it. And before we leave, will you take attendance and say hi?